Inside every computer, the processor operates as a strict rule follower. To execute a command, electricity must navigate a rigid, multi-step sequence. To process a command, the CPU moves it through 4 distinct stages. It fetches the instruction from memory, decodes what the instruction means, executes the actual math, and writes the result back to storage. Looking at this timeline reveals the bottleneck of sequential processing. The CPU waits for the first instruction to clear all 4 stages before it even looks at the second instruction. Because each stage uses a different physical part of the processor chip, this start and stop method creates a massive traffic jam. While the execution hardware is busy crunching the numbers, the fetch and decode components are sitting there doing absolutely nothing. Modern software requires the CPU to process billions of these instructions every second. If every single command takes 4 full clock cycles to finish, a metric engineers call cycles per instruction, or CPI, the whole system is far too slow to run the programs we use today. Engineers realized they couldn't solve this by simply manufacturing faster individual components. To handle modern software, they had to restructure the entire architecture of how tasks are scheduled, finding a way to eliminate waiting entirely. The solution was to treat the processor like a factory assembly line. Instead of waiting for a car to be totally finished before starting the next one, a new unit enters the line the moment the first station is clear. This grid tracks how instructions move through the processor over time. In clock cycle 1, the CPU fetches the first instruction. In clock cycle 2, instruction 1 moves forward to the decode phase. Now that the fetch hardware is empty, the CPU immediately grabs instruction 2. By cycle 3, instruction 1 goes to execute, instruction 2 is decoded, and instruction 3 enters the fetch stage. And in cycle 4, the first instruction finally reaches the write back stage. The pipeline is now completely full. Every physical hardware unit is active simultaneously, working on a different piece of code. By keeping the processor constantly fed with data, there is no idle hardware. Every physical part of the chip is earning its keep. This overlapping architecture highlights the difference between the 2 primary metrics of processor speed, latency and throughput. This highlighted row shows that pipelining does not improve latency. A single instruction still takes 4 full clock cycles to travel from start to finish. We haven't made an individual task any faster. But looking at the right edge of the grid shows us the throughput. Because of the overlap, a finished instruction exits the pipeline every single clock cycle. The processor achieves a cycles per instruction rate of 1. A computer's true power comes from maximizing the volume of completed tasks over time, rather than trying to speed up an isolated command. But this tightly packed assembly line has a strict vulnerability. Its efficiency relies entirely on the processor knowing exactly which instruction is coming next. This breaks down when the code includes an if-then statement, like checking if a password is correct. Engineers call this a control hazard because the CPU is forced to choose between 2 different paths of instructions. This flowchart visualizes the chronological trap. Because the pipeline relies on constant overlapping, the CPU has to fetch the next instructions before the if condition has even reached the execute stage to determine the correct path. It has to guess. If the condition returns false, the processor realizes it guessed wrong, and it just loaded a completely incorrect sequence of instructions into the hardware. To fix it, the CPU performs a pipeline flush. It must throw away all the overlapping instructions currently in the system and start completely over from the other path. Unpredictable decisions in the software can instantly destroy the hardware's carefully orchestrated flow state, dropping the processor right back to that sluggish sequential starting point. To prevent these devastating pipeline flushes, engineers developed a workaround called branch prediction. Instead of guessing blindly, the CPU keeps a history of its past behavior. It uses that data to statistically predict whether an if branch will be taken, loading the pipeline based on that educated guess before the math is even finished. When the prediction is correct, the pipeline stays perfectly full, the high throughput is maintained, and the control hazard remains invisible to the user. The incredible speed of a modern computer is an illusion. It is a fragile, continuous flow, maintained by an overlapping assembly line and a processor that is constantly forced to predict the future.